Hello everyone, I am Yogita pursuing my BE in Sri Venkateshwara College of Engineering. Today I am going to talk about applications of differential calculus in CSE stream. The topics that are covered in this video are what is calculus, what is differential calculus, applications of differential calculus in CSE stream, applications of differential calculus in engineering. Now let us see what is calculus. Calculus is the mathematical study of continuous change in the same way that geometry is the study of shape, algebra is the study of generalizations of arithmetic operations. It has two major branches, differential calculus and integral calculus. The former concerns instantaneous rates of change and the slopes of curves, while the latter concerns accumulation of quantities and areas under or between the curves. These two branches are related to each other by the fundamental theorem of calculus, and they make use of fundamental notions of convergence of infinite sequences and infinite series to a well-defined limit. What is differential calculus? Differential calculus is the study of the definition, properties, and applications of the derivative of a function. The process of finding the derivative is called differentiation. Derivative at that point is a way of encoding the small-scale behavior of the function near that point. By finding the derivative of a function at every point in its domain, it is possible to produce a new function called the derivative function or just the derivative of the original function. In normal terms, the derivative is a linear operator which takes a function as its input and produces a second function as its output. Applications in CSE stream: scientific computing, design and analysis of algorithms, asymptotic enumeration, computer graphics, optimization, probability or statistics, graphs and visuals, applications to solve problems. Calculus is used in an array of computer science areas, including creating graphs or visuals, simulations, problem-solving applications, coding in applications, creating statistic solvers, and the design and analysis of algorithms. Scientific computing: computer algebra systems that compute integrals and derivatives directly, either symbolically or numerically, are the most valent examples here. In addition, any software that simulates a physical system that is based on continuous differential equations necessarily involves computing derivatives and integrals. Design and analysis of algorithms: the behavior of a combinational algorithm on very large instances is often most easily analyzed using calculus. This is especially true for randomized algorithms. Modern probability theory is heavily analytic. Asymptotic enumeration: sometimes the only way to get a handle on an enumeration problem is to form a generating function and use analytic methods to estimate its asymptotic behavior. Computer graphics: in computer graphics and image processing, we also need analytic geometry and linear algebra. Probability or statistics: these cannot be seriously studied without multivariate calculus. For example, machine learning, which makes heavy use of statistics; robotics, where you will need to model physical movements of robots, so we need to know partial derivatives and gradients. Data mining and related subjects also use lot of statistics. Optimization: optimization, non-linear mostly, where multivariate calculus is the fundamental language used to develop everything. Graphs and visuals: we use calculus in creating visual or graphs. Often the graphs or visuals are 3D. They are used often for video games, especially physics engines. Physics engines define the physics in the game such as gravity, friction, etc. Military uses these visuals for simulations, flight and artillery paths, maps, satellites, images, etc. Architects use these visuals for graphing buildings, outlines, etc. Application to solve problems: they use calculus for general problem-solving applications, simulations, and physics engines. Physics engines create realistic situations in video games and probability simulations. The simulations they use calculus to calculate probability. For example, they create programs to solve the integrals and derivatives. In fact, those now are based on the calculator were first simple problems. The computer is used to solve these calculus problems rather than the programmer using it themselves. Video games: in video game development, calculus comes into play in major ways. 3D graphics and illumination, physics engines. By using and manipulating Laplace formulas, Developers can create a 3D mapping of virtual environments and their textured surfaces. Models are also used to apply appropriate shadows, illumination, and refraction to represent the physical world and the objects that move through it. Visualizations. Utilizing advanced algorithms requires calculus such as cos, sine, pi, and e, especially when you are calculating vectors, collision fields, and meshing. Automation. Similar to robotics, automation can require quantifying a lot of human behavior. Hence, as we seen earlier, that calculus has too much involvement in computer science. There is a number of functions of a computer which cannot be performed without help of calculus. Without calculus, we cannot perform any sort of calculus on the computer. So we can conclude that computer sciences is incomplete without calculus. Science and engineering. Differential calculus is used extensively in science and engineering. It can solve problems related to motion, velocity, acceleration, angles of incline or curve on a surface, etc. For example, a car racing driver needs to know the angle at which he should turn his vehicle while negotiating a sharp bend on a racetrack to maintain the desired speed. A plumber has to calculate the gradient of a pipe so that the flow rate of water is maintained at a certain level. Application of differential calculus in engineering. Differential calculus has a wide range of applications in the field of engineering. Some important applications are discussed below. Flow rate. The flow rate of a fluid can be determined by using differential calculus. This is essential for hydraulic systems and other systems that involve the movement of fluids. Pressure. The pressure exerted by the fluid can also be determined by using differential calculus. This is important in understanding the behavior of fluids under different conditions. Velocity. The velocity of a fluid can be calculated by using differential calculus. This is necessary for analyzing the movement of fluids in pipes and other conduits. Heat transfer. Differential calculus can be used to calculate the rate of heat transfer. This is important in understanding how heat moves through materials and can be used to determine the thermal properties of materials. Forces. The forces acting on a fluid can be calculated using differential calculus. Forces are important in physics, engineering, and other fields because they determine the motion of objects or fluids under different conditions. Income. Differential calculus can be used to calculate the rate of change in a person's income over time. This information is important for making financial decisions and planning for the future. Conclusion. Differential calculus is a powerful tool for solving problems and analyzing data. It has a wide range of applications in mathematics, science, engineering, and other areas. Thank you.